So I hope you're all feeling good. The semester is coming to an end. So this will be the last help session, but hopefully we'll cross paths again, like in the next couple of years of your stay at IIT. So today we have bunch of codes to look at. So uh, yeah, like silence your phones and take a deep breath. So we'll focus. Can you all hear me?
Yes, sir.
Okay, cool. So let's start with the pointers. So this is the basic code that we may have seen in the lectures. So here are two variables, x and y, and here are two pointers, p1 and p2. Then we assign 2 to x, we assign 3 to y. Then we make the pointer p1 to refer to the address of x and pointer p2 to refer to address of y. And then we assign the value in the address of p1 to 5 and value of in the address of p2 to 8. So what will this program print? Any thoughts?
2 and 3.
Okay, so one option is 2 and 3.
5 and 8.
5 and
8.
5 and 8. Okay. So yeah, 5 and 8 is the right answer. So basically in at this point it will print 2 and 3 because x is 2 and y is 3. But here what we have done is the address of p1 points to the address of x and p2 points to the address of y. So now when you are saying p1 equals 5, it actually means x equals 5. It's really equivalent. And this is equivalent to saying y equals 8 because p1 was pointing to x and p2 was pointing to y. So we can run this. What is this point? Okay, so indeed it was 2 and 3 initially, and later it is 5 and 8. So I hope this is clear. Let's look at another version of this. So in this one, what we are doing is we are creating a double pointer. And we are this double pointer P is referring to the address of P2. So this is two pointer, double pointer. So that's why since P2 was a pointer itself, the address of P2 will be double pointer. So what we are doing is we are changing the double pointer, the value in this double pointer to P1. And then we are changing the value inside P2 to 10. So what will this print? Anyone?
5 and 10.
5 and 10.
So 10, 10.
10 and 10, 5 and 10. Okay, so we have a few options, 5 and 10. And then, or we have 10 and 10.
So
Okay.
10 and 8.
10 and 8. Okay, so we have all the options now. Yeah, so 10 and 10 is first of all, so here this is 5 and 8, right? So first of all, we can eliminate 10 and 10, right? So 10 and 10 is not possible because we are assigning only one value to 10, right? We are not assigning two values to 10. So only one value is being assigned. Right. So then the question is, what does P2 point to, right? So since P1 is ampersand X, right? So what this means is, so this is essentially saying that we are doing P2 equals P1, right? So star P, since star P is equivalent to P2, so we are saying P2 equals P1. And because P1 is equals to address of X, so we are essentially doing P2 is address of X. So when we assign the value as 10, so it's actually assigning it to X. So the answer 10, 8 is correct, right? So we can run this, and yeah, indeed it prints 10, 8. So what we have done here is using this double pointer, we changed P2 to point to X, right? So this statement, we changed P2 to point to X. So any questions here? Is this clear?
Sir, can you please again explain how the double pointer works in this case? I'm not able to wrap my head around it.
Yeah, so sure. So think about memory, right? So memory is just a linear layout. So you can think of it just a street, right? Whichever street you live on, or IIT Delhi main road, or whatever. So it's just a contiguous street, right?
Yes, sir.
And inside this, you can imagine there are a bunch of houses. So these are like your variables, right? And they can be different sized because of int, char, and whatever, right? So let's say this is m, right? So initially you have x. So let's say x is sitting here and y is sitting here, right?
Yes,
So
sir.
this is your x and this is your y. So then what we're saying is we are saying P1 is ampersand x, right? So what this essentially does is, let's say we, so now this is the value. Now I'm going to put the memory address, right? So, so the same location in memory, this is the location, right? These are locations. And let's say these are addresses. So basically your addresses are simply linear, 1, 2, and I'm just making it simpler. So we are just going to not worry about like integer is 4 bytes and stuff. So let's say this is your memory. Right, so let's say these are your memory addresses which are pointing to so the actual data is what is inside the house, and the address is the address of the house, right? So they are two different concepts. So when you P1 is ampersand x, what you're saying is I'm going to store the address of P1 in a new variable. So let's say this is my P1 now, and I'm saying that the address of x is actually 3, right?
Yes, sir.
So I stored 3 here. Then P2 is address of y. So address of y is 5. So I store 5 here, right? And this is my P1 now. And the next one is P2, right? Right. So then the next types, what I'm saying is P is the address of P1. Right. So let's say I'm storing P here. So this will store 9. Right. And let's say this is my P. Right. So are you with me so far? Right. So pointers please storing addresses. Sorry, P was address of P2, right? And since this is P2, this 5 is P2, so the address of P2 is 9, right? So I stored 9 in P, right? So when I said P is address of P2, I stored 9 here.
Sir, P is equal to address of P2, sir, that we have got from that line int star star P is equal to and P2.
Correct. Correct. So when you write this line, it will basically, so P itself is a pointer variable, right? So P itself is stored somewhere. So P is stored here, let's say. So when you say int star star P's address of P2, so at this point you will store the address of P2 here. And address of P2 is 9, right? Actually, I think these numbers are causing confusion. Let me change them to A, B, C, D, E. Just for simplicity. Right, so here this is basically this is D, right? This is F, and this is now storing J, right? Right, so P1, P2, since they are both pointers, they are storing addresses, and since P is also a pointer, this is also storing an address. And when we said P1 is address of X, so that is why it is storing D, because address of X is D, right? And when we said P2 is address of Y, that is why we are storing F in P2, right? Because address of Y is F. And then when we said P is address of P2, we are storing J, right? Because J is the address of P2.
Sir, so sir, like we declared a pointer P1, why can't we write the same that int star P equal to and P2? Why are we using double star?
Yeah, so because we want to differentiate between address of pointer, right? What is this, right? This is address of pointer variable, right? So this is address of a address, and P2, P1 and P2 is address of integers, right? So we want to differentiate between those, right? So P1 and P2 are addresses of are basically D and F, but they are addresses of these values 2 and 3, right? And similarly, so that is why we want to differentiate. So at the machine level, like when you are down at the assembly and everything, so at the machine level, we will not remember whether it was a int star star or int star. This will be just a bunch of bytes in here, right? But at the language level, so that we don't make any mistakes, that's why we want to differentiate between the two, and that's why C provides you this facility.
Excuse me, sir.
Yeah.
Sir, even at the machine level, it would be different, right? Because a pointer will occupy more space than an integer.
Yes, so pointer will occupy more space, but this double pointer and single pointer will occupy same space, right? So P2 and P will occupy same space because they are really just addresses.
Oh, okay, sir. Got it.
Okay, so I hope this is clear. So we can look at it again. So basically, then when we set star P is equal to P1, so what this will do is star P is basically pointing to is going to change stuff in P2, right? So what this will do is it will change it to whatever value is in P1. So we changed this to D, right? So when we said star P is equal to P1, so since star P, so star P points to J, right? So it will change the value inside J, and so it will change the value inside J to P1, and the value inside P1 is D. So we'll change it to D. Next, we will say star P2 equals 10. So it will go and change what was in D to 10, right? So that is why the value of X has changed. Cool. Yeah, it takes a while to wrap your head around this. It's a bit this is like the most complicated thing in C. But once you understand it, it's actually quite useful, and also it starts to feel obvious, like once you are comfortable with it, which is true for everything you learn, I guess. So yeah, like pointers are basically storing addresses instead of storing values. And when you do star p equals something, it will change the value at that address, right? So when I said star p is equal to p1, it went and looked at the j address and then changed the value inside that address, right? Okay.
Yes, sir. Thank
Uh,
you.
cool, great. Yeah, good discussion. So let's look at another program. We'll look at call by value and call by reference. So we part of it. So here what I'm doing is I defined a local variable x, then I called it, this is called call by value. So I just directly passed x, right? And in this case, I call it by reference. So instead of passing x, I'm passing a pointer to x, right? And I'm just printing the value of x. So what do you think will be printed in both these cases?
Garbage value and 3.
Okay, so in first case, this is garbage value. In the second case, this is 3. Okay.
So I think first one will be 2.
Okay, so we have another option. The first one will be 2. Okay. Any other guesses? And we are all comfortable with this value 3 here. Okay, great. So yeah, let's run this. Yeah, when you run this, it prints 2 and 3. So basically what happens is when you call by value, right? It is copying this value inside the other value. So it is copying x into this other variable x, right? And they are completely different locations in memory because it's just a copy. So we wrote 3 into a new location. So now when I change this x, it doesn't really affect the original x, right? Because original x was at a different location and the new x is a different location, right? So the original x will continue to hold the value 2 because we never changed it. But in the second case, what we have done is we have passed the pointer to it, right? So in this case, this pointer is referring to the original x address, right? So if I draw the address thing again, let's say this is my 2. Right, so here is my x, right? So in the first case, what we are doing is and let me call this y to avoid confusion. So in the first case, in call by value, what this will do is it will copy the value, copy this value inside x into a different location, y, right? So then I'm changing y equals to 3. So it will go and change this y equals to 3 and then return. So this x will continue to stay 2, right? We have not touched the original memory location. And that's why when you print it, you see 2. In the second case, what we're doing is we are passing the address instead. So let's say if I write the address, right? And let's say, so address of x is what? A, right? So I'm passing A into, this is, let's say, my variable p here, right? So p has the value A, which is the address of x, right? So when I say go and change the whatever value is at the address of P at the where P is pointing to, go and change that to 3. So when you say star P equals 3, it will look up A. So it will say, okay, I have to come here. Then I have to change this value to 3. Right. So that is why when you come back out, the value of X has changed to 3. Right. And yeah, indeed, we saw in the first case, the value was 2. The second case, the value is now 3. Right. So any thoughts, questions, comments? Maybe this is not clear. Okay, great. So this is hopefully clear. So yeah, this is like a key difference between call by value and call by reference. In call by value, if you modify the variable, it will not reflect once the function returns. In call by reference, if you modify it, it will reflect, right? Because
So when we pass an array, so is that called by reference?
yeah, so in array, basically it is called by reference. So it is copying the pointer of the starting of the array. And I think you also had an assignment question where binary search was log n. So if you don't do call by reference on arrays, it will be order of n, right? If you're making the copy of the array every time, then it turns out to be order of n. So call by reference is actually also more efficient. But the downside is you have to be very careful that you don't modify things. Otherwise, it will be reflected later on, right? So there are some trade-offs. Okay, I hope this is clear. So let's move to the next thing that was taught this week, to structures. So structures are basically it's just a collection of data, right? So in structures, what we are saying is, okay, this structure point holds two values, x coordinate and y coordinate, and then so then we can start using this, and then I do a type def, so I don't have to write struct point everywhere. So then you can start writing functions that directly takes the entire structure. So in this case, this is taking point P1 and this is taking point P2, right? So if you were not using structures, right, another way to write this would have been this is int P1x, int P1y, int P2x, int P2y. So this is like a lot more tedious, right? As you can imagine, once your structure, so in this case, your structure only has like 2 elements. But if your structure had a whole bunch of elements, let's say 10 elements, so you'll have to pass those 10 elements every time, right? So you don't want to do tedious things in computer science. So here we just put all the both x and y into a structure, and this function can just accept the entire structure and work on this structure directly, right? So, and then while using the function, we can, like here we are defining 2 points and getting the distance between them, right? So basically structures are just a handy way to write like more concise and more readable programs. Okay, so I hope this should be clear. It's nothing fancy here, but let's get to this one. So this one is more interesting. So let's look at the call by reference and call by value thing from a different angle. So here, what we have done is we have defined a big structure, right? So we called it big because this is holding a giant array, and the array in this case is 2 MB. right? So 2 MB of array. Then what we are doing is we are defining two different functions. One is call by value and another is call by reference. So in this case, this is accepting the structure directly. In this case, this is accepting the pointer. And what we are doing is we are calling by value 100 times, and we are going to print how long it takes. And in the second case, we'll call by reference 100 times, and we will print how long this takes, right? So if I run this, so you will see that basically call by value is much slower than calling by reference for this big array. So can anyone guess like why that is the case?
Sir, because the entire character array is getting copied each time.
Exactly. Yes. Yes. So exactly. So here we have to copy this 100 MB. So every 2 MB. So every time we are calling by value, we have to copy 2 MB of memory, right? Which is going to be more expensive. In this case, we are just copying 8 bytes of address, right? 8 bytes is much smaller than 2 MB. So that is why this code runs much faster compared to this code, right? Okay, I hope this is clear. So is there some something maybe not clear here? Yeah, so this is to appreciate, right? Like pointers are so nice, right? Because we avoided this entire copy by just passing the pointer, right? So pointers are very powerful concepts, and so it's like if you want to write performant code, then pointers are useful. Okay. Cool. So let's do I think let's look at a real world, or not really real world, but a bigger program that works well with structures. So we will look at the Pong Auto, this program that we had written, and I'm going to.
Sir, I have a question.
Yeah.
Sir, if we do call by reference and use the const keyword, then it's practically call by value, but we're not copying. So why does call by value exist?
Why does call by value exist? Yeah, so call by value has its own nice properties actually. So it's not, so we don't want to say that call by reference is always great. So call by value has a beautiful property that it is what is called encapsulated, and or also what is called pure function. So this can never really change what was going on in main, right? Right. So main had a value X, and I can be confident that the main will continue to have value X after I call it by value, right? So it can do anything with Y here, but the main doesn't have to worry about what foo well might have done to my variable that I had passed it, right? So this is very important when you think about, like, if you have a really large software which has like millions of lines of code, which is quite typical in industry. And so so this foo well is not even written by you, right? And let's say this is some, like even in our class, if we have 800 students, so some other student has written this foo well. So now, so one option is you go and read all the million lines of code and just figure out what foo well is doing, right? Another option is if I can get some guarantees, if I can make certain assumptions about foo well, then I can reason about my programs in my program in an easier manner. So this gives me a really nice property that I don't have to worry about foo well changing my X, right? So I can just continue to assume that x is equals to 2. But in this case, since I gave it the pointer to the exact memory that I was working on, fooref might have changed it, right? In this case, fooref went ahead and changed this. And I may not know exactly what fooref has done with my memory location. So in such cases, like call by value is good for what is called modularity. So foo-well can be implemented by some other person, by some other engineer, even by some other company, some other industry, whatever. But you can just assume certain things about foo-well without reading its code, right? So it gives better like protection around your memory is still your memory, right? No one is able to touch your memory unless you give its pointer.
Sir, but like if we still use the const keyword, then how would it be? Like I think that will also do the same thing only.
Oh, yeah. So yeah. Yeah. So const is like let me think about it. So const, for everyone else, like const is basically short for constant, right? And it basically means that you cannot modify, you're not allowed to modify the variable. So what is your question again?
Sir, I'm saying that if we use const with call by reference, then it's using it's not changing the value. Instead, it's just not copying it. So why are we separately using call by value?
Right. So the question is, so basically in const, so here since we made it const, compiler is complaining that you're not allowed to modify.
Sir, but in this case, unlike foo-well, we cannot perform operations on the local variable also, right? We are getting no local variable and we can't even change the original.
So you can't write on it, but you can read it. So you can say, let's say if this was doing a square, so, and let's say this was an int. So you can still do star p times star p. So this should still be fine, right? So you are allowed to read the variable. You're not allowed to write the variable, right? So this is still okay. So even though your this thing was constant, you are able to use it, but you're not allowed to write to it. So the question is, if we make it const, then why do we need call by value? Because we are not allowed to change it. Yeah, I'll have to think about this. This is a very good question. Yeah, I'll think about it and post in Piazza. Yeah.
Sir,
Yeah.
I'm saying that if we, for example, took a counter like the array size, then we could directly use it in a loop in foo value. But in foo reference, we cannot change the value of that counter, so we will have to create another variable inside it.
Yeah. Yeah. Okay. So you are saying in some cases you actually want to write it, but you don't want the writes to reflect to the original program. Yeah. To the caller. Yeah, that is a valid reason. But it's still not a very strong reason, because you could have copied the value into a local variable, and then you could have just used that local variable.
Sir,
Yeah.
Sir, but I mean, we can copy it to a local variable, but then ultimately the time taken will be the same here because the process of copying will still happen. So it's like passing by value is doing the same
So,
thing for us.
yeah. So yeah, so it's pretty much like you are implementing call by value on top of call by reference by doing this, right? So yeah. But if you want to like modify the variable, you can directly do call by value, right? So you avoid copying it yourself. Yeah. Okay. Cool. Okay. So let's look at more like a bigger struct example. So this was the Pong program that we had written, which automatically plays Pong, like both the computers, both the paddles are being controlled by the computer. So in this case, yeah, I'm going to make the speed of pedal higher than the ball. So then if I run this, it will continue to play, right? Yeah. So this was the program we had written. So just to get a feel of how we can simplify it using structures. So what we can do is we can create a struct called ball, right? And this ball has x and y coordinates, right? And we can. So just by doing this, right? Like a lot of your functions become bit cleaner, right? So in this case, actually you can also put BR and BC in the ball itself. So this all these things just become ball, right? It's much the code becomes more readable and cleaner, right? So here you can do like ball and change these to ball.r, ball.c, change this to ball, right? Ball.r and ball.c, change this to so yeah, like I hope you can appreciate like this is basically simplifying. So by encapsulating all the information together, we are making the code a bit more cleaner, right? So we don't have to pass as many functions, as many arguments to the functions as before, right? So in all of these, I can just pass the ball itself. Right. So in this case, like the most if you have less code, then basically it is considered more readable. So in this case, we are just reducing the number of parameters we have to pass to every function, right? We can just pass the entire ball. So similarly, we can have a similar thing for paddle, right? And we can just pass the entire paddle instead of passing like P2R and stuff like that. Cool. So I hope this is clear. I won't run this. I must have missed something. So it's not worth the time to debug this, but this is basically the idea. like just by creating this structure, we are able to reduce the number of arguments. So previously this was taking 4 arguments for ball R, ball C, ball DR, and ball DC. By just encapsulating this inside a struct, we reduced the number of arguments. Okay. Okay. So any questions so far? I think we are going to move into some advanced topics that were not covered in the lectures. So anything that we should discuss before that? Okay. So yeah, the next thing, so we have looked at pointers. So another cool thing about C is you can also use function pointers. So here is how you use it. So in here, I'm declaring a function pointer. So this function pointer has to tell the signature. So the signature is basically it returns a void, right? And it takes an integer argument, right? It takes an integer argument, returns a void, and now this is a function pointer. So I can assign it to any function that has this signature, that it returns a void and takes an integer argument. So here I assigned it to the address of fun1, and if the argument passed along on command line is 2, then I'll assign it to fun2, right? So actually, let's run this and see what happens. So let's say I pass it some argument like 0. So when I pass it 0, it prints fun1 10. So in this case, it basically called this function 1, right? When I called this function pointer with argument 10, it called function 1 because function pointer is pointing to the function 1. But if I pass it 2, right, in this case, this function pointer got assigned to the address of function 2, right? So when I called this function pointer, it actually called the function 2 with value 10. So that is why it called function 2. So this is the basic idea of function pointers, that you can dynamically change where the function pointer is pointing to. And when you call a function, when you call on the function pointer, it will call the appropriate function wherever the function pointer is pointing to. So let's look at a more interesting example. So this is like the basic what function pointer is. So let's look at another example with function pointers. So here, okay, so let's say I want to find, let's say I have a bunch of circles, and let me pull this up. Okay, so let's say I have a circle, and circle is a structure. It has a center x, y, and it has a radius, right? So then what I want to do is I want to find the circle which is leftmost, right? So to find the leftmost, I'll do a minimum on the x coordinate, right? X coordinate. So what we are doing here is we are defining a bunch of circles. We are defining a bunch of pointers to the circles. Then we initialize a few circles to some random value, right? And I think size is set to 10. So basically we are creating 10 circles, and we are assigning x, y, and radius to some random values. Then we assign the pointers to the circle in this pointer array, and then we printed. So actually, let me just run this, just this part. So GCC f pointer min. Right. So if I run this has basically created 10 circles, right? So I'm printing circle, center, and radius, right? Cool. So next, what I'm trying to do is I'm trying to find the leftmost circle. So let's call this leftmost. Right. So to get the leftmost circle, what you can do is I'm passing it the array of pointers, right? And then this will return the leftmost circle to me. So what this function is doing is it's just a minimum calculation. So initially the minimum points to the first circle, then it will iterate over the array of circles. Then if the x coordinate is less than the x coordinate of minimum, then the minimum is basically the new circles I, and it will finally return minimum. So if I run this, right, this is showing the leftmost circle. So for the leftmost circle, the x coordinate is 0 as expected, and the radius is 3, right? So are you with me so far? Like, we haven't done anything new here.
Sir, instead of using the dot operator, what have you used?
Yeah, so okay, this is not okay. So this is a pointer to the circle, right? This is not the circle itself. So for pointer, instead of dot, you have to use dash arrow. This is like an arrow, dash and greater than, right? So instead of, since this is a pointer and not the actual structure, not the actual struct, we have used, we have to use this. Okay, any other? Cool. So let's say now what we want to do is we want to find the topmost circle. So this code is good for finding the leftmost circle. Now we have to find the topmost circle. So in that case, we'll have to write another function that looks very similar to this one. Just this condition will change, right? So instead of this condition, we'll have to do like, we'll have to look at y coordinate, right? And then let's say we have to write another, let's say we want to find the smallest circle. So again, the entire code is the same. We'll just have to change this condition to use the radius, right? So as you can imagine, we'll start having copy paste code, right? So this is just a few lines of code, but imagine this was like, there were like 100 different other lines inside this function. So just to change like one line, one small line, we have to copy paste the entire function and find different types of minimums, right? So here is how you can use it with function pointers. So let's look at another implementation of this. Right. So what we are doing is, this first part is the same, but also this is taking a function pointer. What this function pointer does is it compares two circles and it returns the smaller circle, whatever smaller means. So this min f pointer doesn't care about what smaller means. I'll just use this compare function that returns the smaller of the two circles. So then inside I have a loop. This loop is the same, and here I can just say I'll compare the circle with the minimum circle, and whatever it returns is the new minimum, right? And then I can basically call it with two different function pointers. in two different function pointers. So in this one, I'm calling this minf pointer with a function that compares y, and this one is calling it with a function that compares x. So let's look at these functions. What these functions are simply doing is they have the same signature as the compare. So they take two circles and they return the smaller circle. So this one is taking two circles and then it compares the x coordinate and returns the smaller circle. And then this one is taking y coordinate, taking two circles, compares y coordinate and returns the smaller one. So I hope you can appreciate, like in this case, so previously if we had to calculate like different types of minimums, we would have to write different types of min functions, right? In this case, by accepting a function pointer, we made a generic minimum which doesn't care about what the comparison looks like. And then it's up to the comparison to actually do the comparison. And then we have a few choices that we can implement. And we can call it with those choices. Oops. So if I run this, right? So here the first circle is the leftmost circle. This is 0, and the other circle is the top up highermost circle, right? Is giving me y coordinate is 0. So another way of defining highermost could be we further subtract radius from this, right? Because if let's say we are looking at the boundary of the circle instead of the center of the circle, then we can just change this inside this function without having to modify the original min function, right? So I can just change this and it will give me a circle which has the highest tangent or whatever. Okay, is this clear? Like why function pointers are useful? Or maybe this whole thing is lost. Are you with me with function pointers? Hello.
So the benefit of function pointers is that we have to write less code, and we can use the function in different ways. I'm not able to understand it completely, sir. What's the benefit that we're getting out of it?
So the benefit is your code became really modular, right? So as you learn more software engineering, so there is something called open close principle. So what that means is this min function pointer is open for extension and closed for modification. So what that means is you can derive new types of minimums out of this without having to modify this function, right? So you don't have to change what is written inside this function. But you can still derive new types of minimums out of this. So we are not copy pasting any code, and so copy pasting is always bad, right? So I always stress upon that. So copy pasting is bad. So we didn't have to copy paste it, yet we are able to derive new functionalities. We are able to derive new types of minimums without doing any copy pasting. Right. So this is in this case, like, so here, think about this one, right? If you had to do the highermost circle, you would have to write a new min function, right? Which will have the same looping and everything, right? So by function pointer, so this is just one example, but in general, you are able to dynamically change what your code is doing using the function pointers, right? So you could put it in if else and just change what the code is doing using the function pointers. Yeah. So basically, yeah. So min is a short example. So think about sorting, right? Like this could have been sorting, right? Right. Or this could even be yeah, actually, let's try this. So we are further generalizing this code, let's say. So these are all void pointers. I don't even care about whether they are circles or not, right? So I have a very general minimum function, right? It takes a bunch of void pointers and it takes a function and it returns the minimum, right? So in this case, if so, in this case, this could be in a library, right? So I am going to use it for my circles. I can also use it for my rectangles. I can use it for images. I can use it for anything now, just because there is a capability of passing it a function pointer, right? So like here, I can do. I think this should work. We'll see. So I can do circle star C1 is right, and let me just not do my why it is not a struct. Yeah, so there is a warning, but this worked. Incompatible. So let me change this to void pointer. So I am just going to cast this to void pointer, and then there should not be a. Okay, so here. Okay, so this code works, right? So basically what I've done here is now I even generalize this minimum even further, right? So imagine this minimum is is inside a library, right? So this minimum is not even aware of what is a circle. It's not aware of rectangle, whatever, right? So all it is saying is you just give me a bunch of whatever, just give me a bunch of things and just give me a comparator which can compare these two things. I don't know what these I don't know how to compare these things. I don't know, like you can compare it however you want. And but if you just give me those, I'll give you a minimum, right? So then this user comes and they want to use it for circles, right? And they are able to use it first. They're able, so you can like minimum is just 5 lines of code right now. So maybe you're not able to appreciate this. But think about this as a very complex function, right? This is like some image processing, some video processing or whatever, right? So this is some complex function which is saying, okay, just give me a bunch of things and give me your comparator and I'll just give a minimum. So basically, this doesn't care about what is a circle, what is a comparator. It has no idea and doesn't have to. It doesn't have to know. So our user can come and still use this this generic minimum that was written by first of all passing it a bunch of circles and then also passing it a hint on how to compare the circles. So it just passed it that if you give me two circles, I will compare the x coordinate. Some other user can just use it for rectangles. Some can use it for like completely wildly different things, right? Like how do I sort images, find the minimum image. So it can be a very, the same minf pointer function can now be used in a variety of things, right? So you have generalized your code a lot. So this is the benefit of function pointers, and you will see it as you write larger and larger codes. Basically, if you have general purpose libraries, then it's good for them to accept function pointers, right? Because they can be oblivious to what you are trying to do, but still give you a meaningful output, right? So is there some more appreciation of this or no, not really?
Yes, sir. It makes it more general.
Yes, exactly. Yes. So you can do it for sorting, for example, you can try it for yourself. So sorting can be like quick sort, anything, right? So all the sorting really needs is how do I compare two objects? So I can now sort circles, I can sort rectangles, I can sort numbers. I can start sorting everything as long as you give me a decent comparator, right? So yeah, it makes it more general too. Cool. So I do want to cover a bit on memory allocation. So we are out of time, but if you have some other place to go, you can drop off. This session is being recorded. So okay, so let's look at this was not covered, but this is actually a very important concept. So I did want to cover it. So let's look at some dynamic memory allocation and what that means. Okay, so here what we are doing is we are using this thing called malloc to do dynamic allocation. So what we did is we said give me here is an integer and I'll take this integer from the user and I'll allocate that amount of memory. So another way to do this could be to try this, right? So I'll allocate in an array, right? So let's try this first one and see if this works. Right, so it's a very simple program. I think everything should be commented. Yeah, so it's a very simple program that takes input from the user and tries to allocate the array of that size. Okay, so let's run this. Let's run this. Oh, what happened? Something went wrong. Okay. Let's try to allocate like a large size. So 1024 times 1024 times 10. Let's try to allocate 1048560974. Interesting. Okay, so compiler is doing something fancy here. What is going on? Okay, this makes more sense. Okay, never mind. Yeah, so we'll look at the array thing again in later. So basically, yeah, so this is, so when you create an array, this is, we have talked about stack a bunch of times, right? So the array gets allocated on the stack, right? But there's another way to do memory allocation. So malloc stands for memory allocation. Here we are saying allocate size memory or multiplied by size of character. So size of character is 1 byte. So it will just allocate whatever memory the user has asked for, and it will put it in a pointer. So this memory comes out of a different place. So this is called heap allocation, right? And we will explore what that means. But just so you know, like the local variables we had seen so far and the arrays, they were being allocated on stack, but this one is being allocated on a different area called heap. So here I can just allocate some memory. So I allocate 23 sized memory. Then I gave it some input and printed some output. So this is straightforward. Then the nice thing about this is you can also do large allocations. So stack size is actually pretty small. It's just a few MBs, but your heap is actually pretty large. So let's try this one. So here I've set size to 1 GB, right? So size is 1 GB. And I'll first try to allocate 1 GB on array, sorry, on the stack, and then I'll try to allocate it on. So I can, this keyboard is, okay, so I try to allocate a big stack, big array. So this did not work because the memory on stack is just a few MBs. So that's why when I tried to allocate on the, when I tried to create an array of the size, this did not work, right? It gave me a seg fault. So if I do it with the heap instead, right? So this actually works. This is able to allocate 1 GB of memory on the heap. Okay, so that is one nice thing about malloc. You can allocate large amount of memory. So my keyboard is not cooperating with me. Okay, so far so good. We are able to allocate large amount of memory on heap, which we could not do on array. Then another nice thing about heap is it actually stays across function boundaries. So let's see what that means. So here is a function, right? So this is allocating a array of characters, and foo size is set to just 1 KB. So this should be fine, right? We are allocating an array of 1 KB. Then we are putting a in the entire array, and we are null terminating it, and we are returning it. So this is allocating on the stack. What foo heap is doing is it is allocating on heap. So it is, instead of, the only difference is instead of allocating as an array, we are allocating as a malloc, right? We are calling malloc, then we do the same things, and then we return a. So first of all, what do you think will happen in the first case? So this is not using malloc, right? This is just using allocating a array and just printing it. So what will happen in this case? So I'm just printing it, right? So let's look at it again. This foo stack is creating a array and returning that array, and it is putting just a bunch of A's in the array. And then when I come out, I am printing that whatever it returned to me. So any thoughts what will happen? So remember the behavior of stack, right? So when main calls foo stack, it is allocated, there's a new space of memory allocated on the stack, right? And since we are putting an array in here, right, this array belongs here, and then foo stack is returned, so this memory is freed along with the array. So when we come back to main, this is pointing to some garbage value, right? So if I try to run this, if I try to run this, I'll see some garbage value, right? So basically, whatever memory was allocated inside the stack, inside a function is removed. So that is why all the pointers that were pointing to that memory is now garbage. But if we compare it with the other case where we are allocating on memory on heap, so in this case, the allocation actually stays around function boundaries, right? So because basically heap, so there's a call stack, but then there's also a heap. So this heap is independent of this call stack. So when you allocate some memory using malloc, it is allocated in the heap. And now your C is pointing to that heap. So even after this function returns, your C will still point to a valid memory location. So this is actually a very key point. So any thoughts on this, or maybe it's not clear?
Sir, I just want to ask, like we have that new function in C++. So malloc works like that only.
Yes, yes, exactly.
Is exactly same.
Yeah. New allocates on heap as well. Yeah. Okay. Any other question? Okay, so this is nice. Like we are able to allocate stuff across function boundaries. So can you think of something that can go wrong with the with this approach? So basically you allocated some memory and it is living in heap, and now it is always living in heap, right? It will never die. So the stack, the nice thing about stack was when this function got returned, everything this function call did is removed, right? So the memory is freed. But if you allocate on heap, this memory is never freed, right? So what can go wrong?
Sir, if we allocate every variable to the heap, we might overflow.
Exactly, yeah. So basically your computer will run out of memory, right? If you just keep allocating memory and you never release it, we will run out of memory. So for that, it is essential to do free. So after you have done a malloc, this P will continue to live until you free it, right? So in this case, yeah, there's nothing really to see here, but yeah, so yeah, this warning is fine, but yeah, like there's not much to see here, but So what can happen in malloc is if your system has run out of memory, it can actually return null. So you should always, every time you call malloc, you should always check for null, right? So that means your system does not have more memory to give to your program. And and also to not run into situations like this, it's best to call free, right? So you allocate a bunch of memory, you're done with it, then you just free it. Then you allocate some more memory, you're done with it, then you free it, and so on. Right. Cool. So yeah, this is malloc. So any questions? Is this clear? And okay, cool. So yeah, I just want to give a sneak peek into something pretty, just want to leave you with a puzzle. So you can get excited about, there are some very magical things that happen inside computer. So here is a program, right? So I won't be telling what is going on here. This is for you to figure out in the next couple of courses that you take. Hopefully OS, you'll take OS at some point. But here's a program. So this is these are 100 pointers. And what I'm doing is I am calling malloc on, I'm calling malloc over and over again inside while loop. And this malloc is, so size is 1 GB and size of int is 4. So every time it is trying to malloc 4 GB. Okay. And when it, if it's unable to find more memory, then it will return null. And otherwise, and it will also write to the memory. So we can remove the write, I guess. Or actually, let's keep it. So it will write to every location in the memory 3 and it will increment the counter. So we are not doing any free here. Right. So what do you think will happen in this case? So I'll also show you the configuration of my laptop here. So my laptop has 16 GB of memory. Can you see this? My laptop details. Hello?
Yes, sir.
Yes, sir.
Okay, so my laptop has 16 GB of memory. I am allocating 4 GB in a while loop without actually freeing it. Okay, so we will also look at what happens when we run this program. So let's see, I hope it cooperates. So it is going to allocate some memory. So it allocated roughly 4 GB. So one iteration is done, right? Then it allocated another 4 GB. So now we are at more than 8 GB. So we are at 9.12 GB. We are at 11.34 GB, 14 GB, 17 GB. This is interesting, right? So my laptop only had 16 GB of memory. How come this has taken 22 GB already? Right? This should be interesting. So let's look at this again. My laptop had 16 GB of memory, but this program has already taken 36 GB of memory and it continues to run. So yeah, this is some sneak preview into like the rabbit hole that is your computer, right? It goes lot deeper. So yeah, like you will learn about these things in the OS course if you do that. like why this happens, how. So OS is trying to do some magic underneath so that your program is not crashing, and it is able to somehow magically allocate more memory than that is actually available in the system. So yeah, I think this ends this session. Anything else, or we can end the call? Okay, if there are no more questions, so thank you so much. I had a lot of fun with the sessions, and yeah, stay safe. Best of luck with the exams.
Thank you, sir.
Thank you, sir.